So first of all, I'd like to thank everyone who is joining us today. So welcome to the CNCF webinar, so Kubernetes for Storage and Overview. So my name is Daniel. I'm working for Red Hat as a technical marketing manager, as well as I'm responsible for CNCF ambassador as well. So I will be moderating today's webinar, and we would like to welcome our presenter today, the Kiran Mova, the Chief Architect and the MayaData and a core maintainer of OpenEBS and MayaData. So there are a couple of things for housekeeping item before we get started. So during the webinar, you cannot talk as an attendee. So there is a Q&A box at the bottom of your screen. So please feel free to drop your question in there, and we will get as many as we can at the end. And this is the official webinar of CNCF. So as such is the subject is CNCF conduct a code of conduct. So please do not add anything in the chat or question that will be in violation of that code of conduct. So basically, please be respectful all of your fellow participants and presenters. Please also note the recording and slides will be posted later today to the CNCF webinar page, the www.cncf.io/webinars. So I'm gonna hand it over to Kiran for today's presentation. Kiran, take it away.
Thank you, Daniel, for that introduction. Before I begin, I just wanted to snuck this slide in. I'm a huge Game of Thrones fan. And I hope all of you have seen the comet that's right now in our skies. And I had to say that I think CAS is a sign. So we'll learn more about CAS today, the container attached storage. I am going to use the Conway's law a few times. So I thought for those of you who have not heard of it before, it's probably better to kind of just introduce that briefly. I took these images from the .works blog. It basically represents that the kind of system that you develop represents the kind of teams that you have in your organization. And we all know that as we are moving towards more DevOps culture and microservices, we are also having this small, really small, loosely coupled teams. So Conway's law and loosely coupled are things that will keep recurring, and I think it's good to kind of embrace those principles. So I just presented that before we begin the presentation. Today, I'm also joined with Murat and Brian, my co-workers at MayaData. So one of the things is, anything can happen while I am talking today. The internet can go off, and we have Brian and Murat take it over from me in case that happens. We are all available on Kubernetes Slack. In case you have any questions that you want to follow up on, please hit us up on the Kubernetes Slack at those ideas that we have it there. MayaData. So you may have actually not heard of that, or maybe you have, but you would definitely have heard the projects that we develop or projects we are associated with, OpenEBS being one of the first ones that we founded and then donated to CNCF. The most recent one is the Litmus. We also work with a lot of ecosystem projects, especially in the data management space, for example, like Valero and even like NFS provisioner in the Kubernetes 6 org. We are a startup with very highly energetic people who are all well versed with Kubernetes, around 19 CKS, and we are here to talk about the patterns that we have learned from our users about how they have embraced running stateful workloads in Kubernetes. At the end of this session, we hope that we have convinced you that it's not that difficult, and there are like so many new patterns that have come up, and you will be able to, you're willing to kind of try out the stateful workloads in Kubernetes. Just a quick announcement. We and a bunch of our friends at different companies who are working on storage products as well as end user companies have come together. These are all basically early adopters and those who have embraced Kubernetes itself as a data layer. Data on Kubernetes community, it's the first virtual meetup is happening on July 21st, and Dimitris is heading that. He's a great community manager and a builder. If you are part of MLOps, you would know him. Check out that link, and if you would like to participate in any form, please join that meetup and let's get the conversation started. This is a rough outline. There's a lot of stuff to cover, but what I would like to present is the evolution of how stateful workloads are coming to be a common norm in Kubernetes, and what are probably some of the challenges with certain patterns that you follow. And then we present the need for developing container attached storage, followed by some of the benchmarking that one of our partner company has been doing. Mostly like performance numbers and the methodology that we are using to run that. And we'll take up questions throughout. In case you have any questions, please go ahead and post it on the chat window. We'll also have a dedicated time for that. Running stateful workloads in Kubernetes has always been a polarizing topic. It probably still is. This is actually a Twitter thread from 2019 that kind of shows the two spectrums of this notion. The people who kind of say that don't run it, and there are people who think not running in Kubernetes is a joke. And then there are people who are like just getting started and they are looking for some kind of early signs of people running it. So the data on Kubernetes community, as well as like projects like OpenEBS and Longhorn, what we are trying to do is showcase that you can get started with stateful workloads in Kubernetes, and a lot of users have already been adopting that one. This is a survey, 2019 CNCF survey. I think the new one is just about to get published. To be fair, I think it's not just storage. It's networking, security, and a lot of other things can get really confusing when you get started with Kubernetes. A lot of material needs to be available to get trained. Things are getting better. And while people actually tell not to run stateful workloads on Kubernetes, if you look at the landscape and the projects that are actually moving up from sandbox to incubation to graduation, one of the main reasons, or like, one of the due diligence criteria for them to move along is to have end users running them in production on a fairly large setup. So these are all some of the products that are either graduated or are in the incubation or in the process. In fact, like if you ever wonder, if you're running Prometheus or Thanos or etcd in your clusters, you're already running stateful workloads in Kubernetes. These are like a couple of other use cases, and it's actually a lot to talk about. So I've kind of mentioned the links here. This is from a database practitioner who has like decades of experience running Postgres on various platforms, and they are actually recommending that you can run it in Kubernetes now, and they see similar performance numbers compared to like running it in a servers and running it within Kubernetes. And interestingly, they kind of use local PVs, and OpenEBS is one of the local PV provisioners they use. This is completely from an end user perspective. It's not just about database, almost like any stateful stack that application that they've kind of migrated to the Kubernetes. These are what I call as power users of Kubernetes. They're like another reference going down. They embraced Kubernetes early on. They in fact like do their own builds of Kubernetes within their organization from the upstream, and they have a fairly automated setup of like setting up the nodes and all that. One interesting thing to note that is this is also a use case that talks about using LocalPV, but a slightly different variant of LocalPV, which is again like these are end users of OpenEBS. So the thing that I wanted to mention about the LocalPV is, the appeal for the LocalPV is, everything is loosely coupled in the application space, but when it comes to storage, you don't want a shared and a distributed kind of a system. You want as loosely coupled system as possible. So that's one of the appeal towards LocalPV. Here is a long list of companies that have adopted stateful workloads in Kubernetes and are at various stages of running them, and they're like different engines that OpenEBS supports. So some of these applications will be using LocalPV, some a replicated kind of an engine. Yeah, I just had to say that resistance to run stateful workloads in Kubernetes is futile. This one is not just about one or two applications, but you kind of tend to run a lot of your stack. Quickly. It's a different representation. So what's actually made this possible, right? So Kubernetes itself. So though Kubernetes initially did not come across as an orchestrator for stateful workloads, it has evolved with the help of the open source community and a lot of uh, storage vendors as well as the end user community coming together and actually asking for features that will make it easy to run stateful workloads. So if you have been associated with the Kubernetes, you would know the volumes and entry volumes and flex volumes. But most of the folks now might actually just hear about CSI volume. CSI has been great. It's actually standardized the way you connect the storage to the Kubernetes applications. There's still a lot of work that's going on. If you are interested in helping out with any of that work, please join us on the SIG storage channel or one of the working groups that we have, like data protection work group and one of our community calls. So CSI is a key aspect that's actually made many more vendors supplied storage to Kubernetes. This is also like Conway law at play. For example, when Kubernetes started, all the storage vendors that you need to use have to be in the Kubernetes repo, and that kind of made it difficult to even make releases of Kubernetes as well as add new providers and change those storage features and all that. So now with CSI, all the storages can kind of evolve independently, and Kubernetes also can just move along much faster. So this is, why container attached storage. Can't I just go with, using CSI and attaching to one of my existing servers? Yes, this is definitely possible. But as you will see with the remaining slides, this may not be the best pattern for you in case you have adopted the container or microservices kind of approach for your applications, and the moment you do that, you also have adopted the same approach for networking, and why not for storage, right? Also, when I say why not for storage, I think the storage systems that are out there, you need to really look at them and see, are they really refactored to make use of the latest trends that are happening, or they are actually the ones that have been written to work better with the hardware that was there when they were invented, right? And are they monolithic, or have they actually followed the cloud native principles? Those things are some things that you really need to consider. So this is an interesting slide, again, from the 2019 survey, which shows the number of respondents saying what type of storage they use. With Kubernetes, most of the people use storage. So one thing to note about this survey is it just talks about storage. It does not really tell you whether it is about stateful workloads on the Kubernetes or it's the storage for your Kubernetes worker nodes. Probably the first three lines are in that category where you bring up a node, you need some kind of a storage that could be that cloud volumes that you have. But if you look at the other products like ClusterFS, Ceph, Rook, or OpenEBS and Portworx, these are all dedicated to provide storage services for stateful workloads. That actually means a lot of people are already using that in production. Another interesting thing to note that is a lot of people are not afraid to evaluate the container storage approach, and as it is already an open source way, and it's much easier to set it up than a distributed system. So what's happening at the data management layer? I think, again, reiterating that applications have changed, network has changed, and even the way you design the databases is changing as we are, taking the converse layer to the data management layer. This is a great picture, and then I also talk to a lot of users in the community who talk about how their OLAP database that actually has 100 terabytes of data with large volumes is now being split into a Kubernetes cluster running 100 pods with 1 TB volume per database pod. And it's also kind of speaks to loosely coupled teams trying to make their own decisions about the right kind of database that they want to use and not get locked into some database that their platform engineers or the storage engineers have chosen for them. It may not really be right one for their job. So this allows you to treat data as a product. This really good articles on data ops. You should definitely check that out. And there's also declarative data plane that we talk in a blog in CNCF. So this basically splits a monolithic database into multiple databases depending on the services they provide and the applications that they are associated with. For example, in this example, there could be a Redis database for certain services, a MongoDB for certain services, and not have just like one monolithic large database for all the applications that are available in your system. So this is another interesting video that I just thought I'll refer you all to. Talks about an end user, Steven Bower is working at Bloomberg, and he's a platform engineer, and he has to support thousands of engineers. The cool thing is it's an organization that has embraced Conway's law, and it's all about loosely coupled, or what they call as pizza teams, and the applications are obviously in microservices way, and they go down to data management, and they actually embrace the distributed data. They avoid the distributed shared kind of thing, and it has to be isolated and per team database models. I highly recommend you to check that out. So we kind of are talking about Conway's law, and we are saying that this shared architecture is bad. What's really bad with it? Like, a couple of things that I just wanted to highlight here is data gravity. So initially it starts off maybe like a simple one, but what data gravity means is it has a tendency to pull in all your applications towards the data location. So if you are kind of saving the data on your on-premise or like maybe on the cloud, all the applications have to be closer to that so that there's no latency problems to access the data and stuff like that. And once that data grows, as your business grows, it's going to be really hard to break them down and take advantage of any of the cost benefits that you might get, or even like, better architectures that you can build on top of it. You get locked in. This is another interesting trend that is forcing a lot of change in the way applications are architected and written. I'll have more details about it, but the quick point I wanted to make here is the number of cores on the system are increasing, and there's like a huge increase compared to like how it was in early 2000. So 8 cores were like, probably very common, but now they kind of have systems that can support 96 core with 1 TB flash drive and all that. So the thing to note about that is you cannot take an application that was built for an 8 core system and on 96 core machine and expect it to run faster. You need to make use of new constructs to get basically utilize that power and make your applications run faster. So to quickly summarize, before getting into the architecture or like the details of how container attached storage patterns look like, Conway's law is at play at various levels in teams and networks, and even at it's basically changing the culture in which people develop applications. It has to be adopted to the storage as well. It's just a matter of time. And using or getting locked into something is also related to data gravity that we spoke about. A couple of things that I didn't highlight earlier, but it should be self-evident, is the declarative nature that Kubernetes advocates, and which in turn makes GitOps a reality today. Infrastructure as code has been talked about for a while, but we can really visualize this and actually put it into practice, by using projects like Flux is one of my favorites that we use at MayaData as well. Trying to use that kind of an infrastructure with a storage that's kind of outside of the entire Kubernetes declarative plane is going to be really hard. You need like some specialized people taking care of that systems, and maybe like some kind of a manual handoffs or like discussions This all will hinder the automation, and in turn, like, basically autonomy, agility, innovations, it's going to hinder that. We spoke about the cost, so I'll probably skip that one, but a quick one is the power that's available in a node is so much that, maybe sometimes just putting a single local PV may be underutilizing your investment. So maybe there are like some better ways to kind of write the storage engines, even in the hyperconverged model, that can give the right return on investment. So container attached storage is a pattern, and OpenEBS is just one example, as we will see going forward. But in my opinion, it's K8s storage done right. So just to reiterate some of the changes that have happened in the applications, there are like opinions that language should not matter, but languages do matter. Rust being one of the things. You should check out the CNCF Rust at CNCF blog. Highlights how projects within the CNCF, like say TIQV or the one from OpenEBS MyStore and several other projects have rewritten like Linkerd in Rust to take the benefits of the concurrency primitives that are available to operate at scale. So similarly, storage has always been trying to catch up with all these advancements, and that's made the apps themselves distributed. If you look at like the invention of Cassandra, or like you write DB and all these databases, right, or Vitus, for instance, they don't really depend on a distributed shared storage for delivering their services. They can actually work using local PVs, right? So they have moved away from depending on the underlying storages for replication and high availability, and they've built all of that within them. That's an interesting food for thought. I think how long they can go or how far they can go with this approach. What are the complementary things that you need to provide to these applications is a good discussion to have. Agility is the main factor that's driving them. So specific to IO, I think all these changes in the application layer itself have changed the way you provision the volumes. We spoke about 100 TB volume getting broken down into 1 TB. Actually, in fact, like if I look at the history of like the volumes provisioned in OpenEBS, 1 TB is quite big. So most of the times for your ML ops or like, for your CI/CD pipelines or some of the observability stuff that you run in Kubernetes, 200 GB will be max. And there are also volumes that get created just with 5 GB as well. The thing that differs in this Kubernetes model is the volume of the volumes that you provision is very high. So how fast, for example, like if you go to the 6 storage channel, there was just one question floating around about, I'm provisioning 30 volumes and it's slow to provision on that particular machine, right? The next one is the IO patterns and the capacity requirements have changed. Similarly, like the hardware that powers the storage systems is changing. I think you must have heard about NVMe, DPDK, and SPDK. I have a brief slides in this presentation, but a detailed link I have in a different presentation or a webinar that we did recently. So just to highlight on those hardware aspects, this is an interesting one. So as a member of, we all know about AIO as a way to gain higher transaction processing power, but then with the AIO, you kind of reach a saturation once you cross 8 cores. And that's where IOU-ring and IOU-ring poll methods, the changes that went into the Linux kernel are helping gain much more number of transactions per second. This is an interesting chart from Brendan Burns that talks about the impact of the system calls or the faults that can happen on the performance. So some kind of a notion here is that if your application makes more than 5 system calls, then the latencies tend to increase. And the latency could increase for several reasons. It could be like a hardware bug, or it could be because of the locks that are maintained, the locks that are implemented within those different drivers. So one of the mitigation plans could be to move towards a user space, and to move to user space, there are other dependencies. That's where NVMe kind of comes into play. If you tend to go into user space with using the traditional drivers that run on SCSI, the performance can actually drop. You will see in the numbers that I present later as well. But with respect to NVMe, the numbers in fact can grow. You can actually bypass the kernel altogether from your app. That's possible with PPTK and SPDK. So one interesting difference that we need to note between the SCSI or SAS way of doing things and NVMe is SCSI can top at the 1024 commands processed per second versus 64K commands that an NVMe can process, right? So can we go back to the previous slide, please? This one is an interesting one that kind of lists a few of the things. I think I just mentioned about linkerd and like TIKV that being written in Rust. There are other examples here, for example, like in the networking space, like VPP, Open vSwitch, they are all getting some kind of a partial rewrite of their stack to make use of the better hardware, especially going towards the pole mode drivers. So we should have established by now that there is some amount of rewrite to the technology stack that we have to write in case we want to get returns out of our investment into the latest hardware, as well as there are the technologies available, and there are already early adopters and sample projects that have gone ahead. In fact, like if you look at technologies like CEF, right, that have been around for a while, have attempted to approach this problem and try to rewrite. I think they skipped the NVMe refactoring, but they've definitely decided at least like they'll take the roots DB. So that's another. It's there in the roadmap of not just the distributed systems like CEF, but even like Cassandra. If you look at their community call and the roadmap, you will notice that they're talking about a refactoring of their stack to better run in Kubernetes. So Cassandra is probably an example of a distributed app, or no, not probably, it is a distributed app, which has a way of maintaining resiliency and high availability by talking to each other at the application layer. These are typically deployed as stateful sets in Kubernetes, and all they need is like a local PV that can be attached. So how are these local PV provisioned? I think almost all the storage in all the Kubernetes itself has a local PV, but there are a lot of variants and enhancements that we can do on top of that. That was one of the requests that came into the OpenEBS community, and that's why we have these different variants of local PVs. If we go to the next one. This kind of shows the architecture where you can have different types of Kubernetes worker nodes. If your Kubernetes worker node is a node with very limited extra disks, then you would want to use a local PV that's based on a host path provisioner, which dynamically creates a directory for you with the data, which is completely isolated from other workloads. It does not have the security risks of like, sharing the data across different pods. And the path is completely hidden from different namespaces and even from the application developer. That's about the local PV host part. And then you have like, let's say like you have machines like the NVMe machine that I showed with 96 cores, which can actually have a lot of disks, NVMe SSDs attached to that one. Those you can use the local PV, and one component of OpenEBS, which is a generic component not tied to OpenEBS, is called as Node Device Manager, that can be put on any Kubernetes cluster. It will help you discover all the block devices that are available, and you can kind of use the block device claim to get a block device and provide that as a local PV to your application. That's the block device provisioner. So one thing that I mentioned earlier was around, if we use local PV, how long can we go? And I think we get into a little bit of a data lifecycle kind of scenarios, especially when running applications that last longer. Actually, many of the applications within Kubernetes are ephemeral. They kind of come and go, but there are some applications that run for longer duration. So for those, taking backups and making sure we are able to migrate to other locations kind of becomes important. And that's when LocalPV kind of falls a little bit short, and you kind of use an application like ZFS pool you create on a node and you carve out the volumes that will help you uh, provide incremental snapshots as well as block transfers at a much faster rate than the raw block device. All the three have been hugely popular within the OpenEBS community than the replicated engines. It's worth checking out some of these. I think it just takes a minute to kind of get started with them, and then you can run your stateful application with that.
Kiran, can we pause here for just a minute and take a couple of questions that have come in?
Sure.
Great. First one is from Ravi Kumar, and Ravi Kumar asks, what are all the security aspects that we need to consider when we go with stateful workloads in container attached storage? Can you comment on the security angles?
Yeah. So the security aspect, that you can kind of divide that into multiple layers: data security at rest, security at access path, security at the in transfer of the data between the storage pods itself. So all of this, for example, like access part is controlled by the Kubernetes RBAC plus the storage access protocol security itself. The transmission is at a block layer replication. So it's you can kind of set up additional encryption keys that you can protect your data from even getting mounted. Even if somebody gets logged in, you can kind of protect them from mounting that particular volume. Actually, a lot more about this is discussed in the Maya store. If we can kind of follow this up on the Slack channel, we can provide more details. And
Great,
just quickly on the rest, at rest, you have different strategies that you can apply as well.
And we have another question from Bisser about read-write-many support. If you could address that read-write-many question.
Awesome, that's a great one. So most of the storage engines that we provide are at a block level, but we use NFS, the one from the Kubernetes external storage, as an additional operator and a provisioner that runs within Kubernetes to provide the RWM capability.
Great. And one more question. Can you please dive into what a ZFS pool is and how it gets defined?
Awesome. So ZFS is an copy on write file system technology that's been around for a long time. And actually we kind of chose that because of its resiliency and auto error correction capabilities. If a disk fails, it has a software rate kind of a functionality, and it also has encryption support built into that one. So you can it is mainly targeted at application workloads that need snapshot capabilities, encryption capabilities, and also protection against individual disk failures. And you can kind of use this to create volumes with thin provisioning, and you can kind of grow the ZFS pool by adding more disks to the node if that's a possibility for your Kubernetes cluster.
Great, thanks for that. I think that does it for our questions for now, but everybody should feel free to ask further questions in the Q&A box.
Awesome. So now, for distributed apps, the pattern for LocalPV is best suited, but there are also some applications that do not have inbuilt replication capabilities or like a cluster mode support yet. It is possible that they are working on it, or like new operators are coming up. Even for those applications, we can kind of use this replicated but isolated pattern, where each of the application gets its own target pod that receives the IO request and then takes care of replicating that data into multiple nodes. And if that node fails, the target pod just moves to a new node, and then the application can connect to that particular target and access the data. These are like some engines that we have. GY was one of the first engines that we developed. CStore was the second one, which is again a variant of a ZFS. We love ZFS. And the difference between ZFS and CStore is ZFS is a kernel module, and CStore is basically a port of ZFS into the user space, and we run ZFS in user space as part of the CStore engine. And then the new one that we just added is Maestro, that's mainly targeted to make use of the hardware benefits that we have around NVMe and all that. Longhorn is a separate project in itself. Even before Longhorn started supporting Kubernetes, we kind of had a fork of it, and that actually resulted in like two independent projects being built. But the core engines remain the same. So this this dives into a little bit more details on how the CStore engine works. So you typically have your PV that is represented by a configuration, and if you look at that configuration, you will see a service IP, a Kubernetes service IP, which points to an iSCSI target. The choice of iSCSI target was mainly to make sure that we use an access protocol that was available on most of the Kubernetes clusters, or like the operating systems that we have out there. When we started off this project like 2 years back, I think the NVMe support and all that was in the early stages. So this provided a way for us to demonstrate that container attached storage is actually a pattern that works, and it's been hugely successful in terms of getting a lot of users and helping us learn a lot about what it means to really write storage engines in user space. The learnings of that we have kind of incorporated into building MayaStore as well. So the iSCSI target will take the request and then kind of convert that into blocks, attach some metadata, and push it onto the replica pods, which are like CStore pods, completely user space pods running on different nodes. These metadata that we add help us to determine the, for example, like if one node goes down, how, and that comes back, how to rebuild the data from the remaining available nodes. So one thing to note here is every application gets its own target PV, unlike, let's say, like a distributed system that also could support something like this, but all the IOs will have to go through a common meta management layer that actually runs some algorithm to find out the right node, and that's kind of becomes a shared. In this one, the engine is replicated, the data is replicated, but it also has the isolation at a per workload level. This kind of summarizes like the benefits that you get of using container attached storage pattern. So you basically now have eliminated the need for maintaining a shared infrastructure for your autonomous teams, helping them to kind of become more agile. So different engines for different workloads. It's not like some unified engine that supports everything. You kind of choose what you want, and this can all be done via storage classes and configuration YAMLs. Even we can write some kind of a policies that can pick up the right storage engine for you. And it's completely open source. It's part of the CNCF, and you also have the right architecture in terms of storage engine for NVMe. So go ahead. These are some of the projects that we have. I think the OpenEBS and Portworx are the ones that you already saw on the CNCF survey. OpenEBS and Longhorn are completely open source. StorageOS, Portworx, and Robin are the commercial closed source offerings that we have. But all of this follow the container attached storage pattern. So we already talked about the benefits. I just wanted to highlight one specific thing, and it's kind of important. With the container attached storage pattern, you have a very limited blast radius. So what I mean by that is, if you are running a distributed system and then couple of nodes that are running a metadata goes, or like, even the actual data nodes go away, then all the nodes end up participating in rebuilding that, and then that can actually degrade the system, or even like put more burden and cause a ripple effect on the failure of the disks. In fact, like if you have been in the storage industry and like watched the incidents that come up, sometimes a single SSD can bring down the entire availability zone. I think this has been published in some blog that I think Cortex recently published about why they caused a downtime. It's pretty interesting to check out. But with using this isolated technology, you kind of limit the number of workloads that you impact with that one. So I think this should be the question, especially because we are advocating for running in the user space and running within Kubernetes. That's kind of that's along with the applications. How would the performance look like? I'll get into the numbers in a bit. But by this point, we should know that any high intensive workloads that are distributed tend to use LocalPV where they don't have any degradation. And then there are applications that need some kind of replication from the storage system, but this may not be like highly sensitive or IO intensive. So for those, C-store is good. In fact, like we have this use case where new workloads get created for translating web pages, and there are like around 50 workloads running at a time for running those kind of setups. And they all run within a 3-node cluster with 2 disks on each node. And yes, MayaStore is the new engine that we have that is actually targeted for workloads that have high IO demands. We are at 020 and we are under active development. We would welcome your feedback. This is actually a good webinar from the maintainer of the MayaStore on how the internals of how MayaStore has been implemented. Please do check that out, and really excited about that kicking off. Cool. One of the things about performance is, we can always run it as project maintenance and we can get biased, and we know that the numbers are great. So Ben Hundley from Octane has been helping us run some independent performance benchmarking on the different storage engines that we have in OpenEBS. One of the cool things about Octane, I think you should definitely check them out. They are also a company that's trying to solve the cost problems on Kubernetes. The tests that that Ben has done and the scripts for running those tests are all open sourced in the link that I've pasted there. It's a couple of tests, that one for checking the demands from an application. So it's basically Postgres is used as an application here. So pgbench is the tool that we use, and FIO is another standard tool that typically users run for benchmarking the applications. The way to do FIO with pgbench is you kind of generate the pgbench profile and use block trace to kind of capture that trace and replay that with FIO, so that you can kind of reproduce that workload characteristics multiple times. All the scripts, the Terraform scripts, as well as the FIO and pgbench commands are available in the repo. Do check it out, or if you want to contribute more to this test, please reach out to us on the Kubernetes Slack or on the repo via issues, and it'll be great. So one thing to note, so we wanted to keep this as simple as possible, and we want to work towards a configuration where, sane by default is the thing that we use in our discussions, contributor discussions. So we asked Ben to run with the default settings that there are. We have not provided any tunings for any of the engines, but if you do run tests on an iSCSI, these are like some tunings that will help you get more performance out of iSCSI devices. For example, increasing the number of sessions. I think the default is 256, changing it to 4096, and also increasing the number of sessions just to establish and setting up a multi-path. These are all like some ways to enhance the performance of iSCSI sessions. So by this point, we must have realized that CAS is about per workload. It's not about a single volume serving a database for all the applications, but it's about the scale. So the tests really should be focusing on the scale and the efficiency of those when data operations are in progress. Here we are actually partnering with Conway from D2IQ and for example, like Rancher to help with the overall managed Kubernetes space where you kind of set up the nodes the right way. And I think it's great that Terraform has come up with Terraform for Kubernetes that will, to run Kubernetes, you need to have the nodes pre-configured. And these are all tools that only power users had, like the one that I mentioned in Optero, but now it's becoming more accessible for everybody. Once you have that node set up, it becomes easier to kind of run this optimized test. And then chaos is another thing. Microservices are hard when to debug, and it's better we kind of introduce this chaos. Litmus is the project that just went into Sandbox, which helps you to introduce chaos in a cloud native way or a Kubernetes native way, just using custom resources, and you can kind of set up the chaos charts available for all the popular projects. You can use one of them or write your own chart as well. So this is the first chart that I have regarding the workload. So this is a Postgres replay that we have applied. The comparison is between the host path, device, CStore, and the MayaStore. I did not take the ZFS LocalPV or the Jiva in this test, but we plan to add them soon at that repo. So this kind of shows that running in the user space for CStore did degrade the performance. But again, like, it also uses iSCSI and it's not tuned for like providing a better performance. But even if it's the lower numbers, we'll see the IOPS that it gives in the next slide. One other thing to note here is the MayaStore is also running with iSCSI, but it's comparable because of the pole mode driver way of processing the IO request. It's at par with LocalPV numbers. So with respect to CStore, even though the bandwidth looks really low, the number of IOPS is at 1,000 or 2,000 for writes, which is typically the IOPS that you kind of get from cloud volumes as well in your traditional labs. And for less IO intensive workloads, this is still suited, and that's why we have like a lot of customers using CStore still. But we are committed to increase that performance, and for other workloads, that's why we started working on MayaStore. So these are like a few other numbers that we have. Again, this is like random read-write numbers. We have seen the numbers go up by doing some tune, by setting some iSCSI tunables, but this one is without the tunables. You can try out by increasing the number of sessions and checking that one. This is with sequential. Again, it's not tuned in any way, but with sequential, MayaStore performs better than the LocalPV itself. All right. So we spoke about a lot in terms of the container attached storage, which is basically loosely coupled storage, enabling small autonomous teams deliver faster, even their basically deploy the stateful workloads in such a way that they can drive their innovations faster. Once we are Kubernetes, one Kubernetes cluster is just, it's a part of a bigger thing, right? We need to work with multiple clusters or sometimes even migrate the applications across clusters. That's where the true data agility comes. And for example, it's a bigger problem that OpenEBS alone will not tackle. There are like a lot of other projects or companies that actually help out here. For example, like Velero is one of the projects that we contribute to and also take, kind of integrate with OpenEBS for doing the migrations from one cluster to the other cluster. The projects like we have Tanzu and Kubera that I think Murat will talk a little bit more about to help us. Before we go there, I could probably take some questions.
It doesn't look like we have any further questions.
Kiran, I think we do have a couple of questions. So I think the one is from Vishal Paul, performance of local disk versus PVs in Kubernetes. That's the first question.
Cool. I think that's just answered
Okay.
with the performance numbers.
Okay. And another question we have is from Rishi. How do you manage on dynamic provision?
Right. So there are some high-level operators that we write, Rishi, for setting up these things. And I think Murat is going to touch upon that a little bit now. Murat, over to you.
Thank you so much, Kiran. And this is Murat. And yeah, a lot of information to digest here. With respect to time, I will go over Kubera a little bit. This is a new offering from MayaData, our commercial offering. But also free, available forever for SaaS usage. So at MayaData, we develop data agility tools, and OpenEBS is one of them, and also chaos engineering tool, Litmus is another. But when we talk to users and community, of course, our developers as well, all we care is our application. And Kubera's focus is exactly this application. So we created a solution which bundles all the data agility tools and gives you flexibility running multi-cloud, multi-team environment, and enables more workloads on Kubernetes. And so Kubera, like I said, it's available as SaaS and also on-prem. Many enterprise users now using Kubera on-prem environment. So Kubera equips you for the pretty much rest of it. So it runs on any Kubernetes. You can add your existing cluster into Kubera, and then you get policy-based storage. And it also simplifies management, installation, provisioning of OpenEBS, upgrades of OpenEBS. And I have a couple of screens to share here. And not limited with this, but Kubera also gives you off-cluster log storage. This is also available in the free basic plan forever. One mistake we see sometimes users do, they are running their EFK stack on the same cluster, which logs you need most when you don't have access or something goes wrong with the cluster. Kubera helps to store and then gives you managed EFK stack just by adding your cluster, and this runs on offload cluster, and you can manage multiple clusters even if they disappear, and then you can still have access to your logs, and also helps you to turn Kubernetes into data layer, helps to thanks to OpenEBS and other components, open source components that are baked into Kubera. So helps you to provision volumes and have visibility into device management put together. Sometimes might be complex for not YAML savvy users, how to put these storage pools together. It detects your disk using NDM, and you create simply pools, and also gives you a very advanced topology view, so that can be used in multiple use cases. One is, of course, troubleshooting. You can see the high level picture of your connected Kubernetes clusters, and then you can also use it to troubleshoot, let's say, service mesh issues, or dive into your per system volumes. And from this screen, you can see here little camera icon. You can take a snapshot and then clone your volumes, and then do a lot of creative things, and then also get into direct access into your pods logs, and pretty much to use it for troubleshooting, and also so you can use Kubera for your disaster recovery strategy, to build your disaster recovery strategy. Everything on Kubera is application centric, so we also give you application monitoring tools. Most of the stateful workloads are auto discovered on Kubera, and out of box we give you, let's say you have a Minio workload running or Postgres running, we manage the collector exporters for you and deploy on your cluster and give you relevant Grafana dashboards, and as well as then from that view you can also take a backup of this workload on S3 backend, cloud or commercial S3 compliant backends, and then use that backup as a DR case, or also you can use it for data migration use case. So that backup you take on S3 can be restored on the same cluster as well as new cluster. And we see this trend increasingly. Instead of upgrading Kubernetes clusters, user deploy. Some users, we even see that in our stats, they deploy Kubernetes cluster every day, and instead of upgrading them for many reasons, and they deploy a new cluster and migrate their workloads. And this is a high level of what's in Kubera. Of course, it is all open source, and OpenEBS, Litmus, and many other CNCF projects are in the core of Kubera. And then as a basic user, you get all this capacity reporting, data management, auto deployment, features provisioning. And when you move to standard and enterprise, you get all the advanced functionality, topology views, chat apps, application discovery, and then DR, multi-vendor data management.
Murat, if I could stop you there on that last slide. We have a couple of questions that have come in, and I thought it might be a good time to answer them. A couple of them are about how it's possible that MayaStore can go faster than LocalPV. Could you or Kiran address that one?
Take that, Kiran, or
Yeah, I think I just posted the answer in the channel, but I'll just repeat it. So the way the MayaStore performs the writes to the disks, it uses the port mode drivers that makes it faster compared to, let's say, when we use host path, we kind of put XFS drivers on that one. So that's the difference. If you're writing directly into MayaStore, it is faster than writing into an XFS and going through those layers.
Great, thanks for that. And
is there a streamlined process to install, configure out of 3 CSI drivers for various providers? Is that a manual process fundamentally? I will take this as a Kubera question. So what we do in Kubera also provide that. I think you can see somewhere here, yes, CSI lifecycle management. Well, what we see is also the CSI is a moving target, and you need to maintain your drivers exactly like you asked. And then for top cloud vendors, so we also plan to implement this and provide kind of southbound provisioner to OpenEBS and Kubera, but at the same time, well, to be able to do that reliably, you need to maintain the installation of CSI drivers, and then Kubera will provide that CSI lifecycle management. Hope that answers the question. And has the anonymous poster ZFS question has been addressed? I'm interested in that as well, asks Alex. And let me go back. Can you please dive into what ZFS pool is and how it gets defined?
Right. So the ZFS pool definition itself, it's out of the CSI driver that you can kind of create using your Terraform scripts or Ansible scripts. And we also have a roadmap item on that one to automatically create it, especially if you would want that. But most of these power users, like I said, they have some scripts already. They create the ZFS pool on each node with a set of disks. And in the storage class, they kind of mention the pool on which the volumes have to be provisioned. That's how you get that one. I posted the link to the ZFS LocalPV on the chat window. If somebody is interested, please join the discussion over the issues or like on the Slack.
I think that answers the last question. And then before I hand it back to Daniel, last slide on Kubera. So Kubera runs on any Kubernetes and 100% in user space, and also automates all the operations and then turns Kubernetes into a data layer. The benefit of it is, of course, comes with 24 support, and you can run it as SaaS or on-prem. You get all this data migration, resilience, compliance, logging, topology, alerts, analytics functionality. And of course, Conway is low, so multi-cloud, multi-team is a big thing in DevOps culture. So we see a lot of small teams, small workloads, loosely coupled, but when they grow, not the team, but number of small teams, as a corporation, even for startups, sometimes our cloud costs or sometimes management gets out of control, and Kubera is targeting to do more on that space. And then you can manage different engines per workloads, and also you can share your clusters across teams. That way, well, you have a backup, an S3 backup of your workload on one cluster. Another team can take that workload for various use cases. ML and data science is one of them, very popular, but can recover it on their cluster. I think we have a new question. No, I think it's all answered.
Yes.
Back to you,
No.
community.
If anyone has any further questions, please submit them via the question interface.
Yeah, just a shout out that again, for those who joined late, that data on Kubernetes community is getting started, and the first talk is from Patrick from DataStax on July 21st. Please join there. And we are all available on the Kubernetes Slack, OpenEBS Slack channel. Please feel free to hit us up.
So much for everyone joining us today.
Oh, great. That is really awesome. So thank you, Kiran and Mira, Brian, for great presentation today and Q&A facilitation. So all right, so that's all right. The question we have time for today, and actually we're already out of time. So yeah, thanks for joining us today. The webinar recording and slides that will be online later today in the CNCF webinar page. And we are looking forward to seeing you at the future CNCF webinar as well. So have a good rest of the day. Thank you.